Hello there. Beneath your feet, far below the surface you stand on, the Earth is not quiet. It is moving, heating, and slowly changing, every moment of every day. Volcanoes are one of the few places where this hidden world briefly reveals itself. They are not just mountains that erupt. They are openings into the planet's interior, shaped by heat, pressure, chemistry, and time. Most people think of volcanoes as sudden explosions, but in reality, they are long processes. They begin deep underground, long before any eruption is visible, and they continue long after lava cools and ash settles. Volcanoes have built continents, altered climates, destroyed cities, and enriched soils that humans still depend on. They are responsible for some of the most fertile land on Earth, and some of its most dangerous moments. In this video, we will not rush from eruption to eruption. Instead, we will slow down and examine how volcanoes actually work, where magma comes from, why pressure builds, why some volcanoes flow gently while others explode violently, and why these events follow patterns, not randomness. Along the way, we will look at real historical eruptions, not as tragedies, but as case studies that help us understand Earth's internal behavior. We will also see how modern science monitors volcanoes today, and what these processes tell us about Earth's future, and even other planets. But before we begin, if you value long-form, knowledge-driven videos that explain complex ideas clearly and patiently, you can support the channel by liking this video, subscribing, and sharing your thoughts in the comments. Now, let's begin by answering a simple question that turns out to be far deeper than it sounds. What is a volcano, really? A volcano is usually imagined as a mountain that suddenly erupts, sending lava and ash into the air. That image is familiar, but it only captures a small part of what a volcano actually is. A volcano is not defined by the moment it erupts. It is defined by a long, hidden process that begins deep inside the Earth. At its simplest level, a volcano is a pathway. It is a place where material from within the planet slowly finds a way to move upward. This material is not fire, and it is not freely flowing liquid rock. It is a complex mixture of molten rock, solid crystals, and gases, all shaped by pressure, temperature, and time. The Earth beneath our feet is not solid in the way it appears. The surface is rigid, but below it, the planet behaves very differently. Heat trapped inside the Earth causes rock to soften and move, not quickly, but gradually. Over enormous spans of time, this movement becomes powerful enough to shape continents and open pathways to the surface. Magma forms when rock inside the Earth partially melts. This melting does not require the rock to turn completely liquid. Even a small amount of melt is enough to change its behavior. Once melt forms, it becomes slightly less dense than the surrounding solid rock. That difference is small, but it matters. It allows magma to rise. This upward movement is slow and uneven. Magma does not surge toward the surface. It moves through cracks, weak zones, and fractures in the Earth's crust, sometimes pausing, sometimes changing direction. Much of the time, magma never reaches the surface at all. It cools, hardens, and becomes part of the crust. Where magma movement becomes focused and repeated, a volcanic system exists. This system includes a deep source of melt, pathways through solid rock, regions where magma can temporarily collect, and sometimes an opening at the surface. The presence of this system is what defines a volcano, not whether it is erupting at a given moment. This is why many volcanoes appear quiet for centuries. Some never erupt within recorded history. They are still volcanoes because the internal conditions that allow magma to rise are present, even if nothing dramatic happens above ground. Volcanic activity is also far more common than most people realize. Much of it takes place beneath the oceans, where magma emerges quietly along long cracks in the seafloor. There, new rock is constantly being created, reshaping the planet without explosions or headlines. On land, volcanoes take many forms. Some are steep and tall, built from layers of ash and hardened lava. Others are wide and gently sloped, formed by lava that flows easily and spreads far before cooling. These differences are not accidental. They are controlled by the composition of the magma, the amount of gas trapped within it, and the structure of the crust it moves through. Volcanoes are not random disasters. They are surface expressions of deeper planetary behavior. They release heat and material from inside the Earth, helping regulate internal pressure over geological time. In doing so, they reshape landscapes, influence climates, and alter the conditions in which life develops. To understand volcanoes, then, is to understand how the Earth moves, stores energy, and slowly changes from the inside out. To understand why volcanoes exist at all, it helps to stop thinking of the Earth as a solid object and start thinking of it as a layered system, each layer behaving differently under heat and pressure. Everything that happens at a volcano is controlled by how these layers interact over long periods of time. The outermost layer is the crust. This is the thin, rigid shell that forms continents and ocean floors. Compared to the size of the planet, the crust is extremely thin, more like a fragile skin than a solid wall. It can crack, bend, and break under stress. These weaknesses matter because magma can only move upward where the crust allows pathways to form. Beneath the crust lies the mantle, a vast region that makes up most of Earth's volume. The mantle is hot, but it is not fully molten. Most of it is solid rock that behaves in a slow, flexible way over geological time. Under intense heat and pressure, mantle rock can deform and flow, not in minutes or hours, but over thousands to millions of years. This slow movement is driven by heat. Some of that heat comes from Earth's formation, leftover energy from a time when the planet was still assembling. Another major source comes from the radioactive decay of elements deep within the Earth. Together, these heat sources keep the mantle warm enough to remain active. Within the mantle, heat does not stay still. Warmer material becomes slightly less dense and begins to rise, while cooler material sinks. This continuous circulation is known as mantle convection. It is not violent or fast, but over long time spans, it moves enormous amounts of rock and energy. Volcanoes begin when conditions allow parts of the mantle to partially melt. This melting does not happen simply because rock gets hotter. Pressure plays a major role. In some regions, pressure decreases as mantle material rises closer to the surface, allowing melting to occur even without a large temperature increase. In other areas, water introduced into the mantle lowers the melting point of rock, making magma formation easier. Once partial melting begins, liquid magma separates from solid crystals. This liquid is less dense than the surrounding rock, which gives it a slow upward push. The movement is subtle but persistent. Magma migrates through tiny spaces, fractures, and weak zones, often changing direction as conditions shift. As magma rises into the crust, it rarely travels straight to the surface. Instead, it often accumulates in magma storage regions, sometimes called magma chambers, though they are not empty caverns filled with liquid. These regions are complex mixtures of solid and molten material, constantly evolving as magma cools, reheats, and mixes. Deeper still is the core, which does not produce magma directly, but plays an essential supporting role. The intense heat of the core helps drive mantle convection, sustaining the energy flow that makes volcanism possible over billions of years. When these layers are viewed together, volcanoes stop looking like surface accidents. They become natural outcomes of Earth's internal structure, places where heat, pressure and material movement briefly intersect with the surface. The words magma and lava are often treated as if they describe two different substances, but scientifically, they describe the same material at different points in its journey. The distinction is not chemical, it is environmental. It depends entirely on where the molten rock exists and the conditions surrounding it. When molten rock is beneath the Earth's surface, it is called magma. At this stage, it exists under immense pressure. That pressure keeps gases dissolved within the molten material, preventing them from expanding. Magma is not a simple liquid. It is a mixture of molten rock, solid mineral crystals, and dissolved gases, all interacting constantly. This mixture is unstable by nature. Magma exists close to its melting point, meaning small changes in pressure, temperature, or composition can significantly alter how it behaves. Deep underground, pressure dominates. It suppresses gas expansion and keeps magma relatively contained. As magma begins to rise, its environment changes gradually. Pressure decreases as depth decreases. This change may seem subtle, but it has enormous consequences. Gases that were once dissolved begin to separate from the molten rock. Tiny bubbles form, grow, and interact with each other. The ability of these gases to escape, or become trapped, plays a central role in determining how a volcano will behave. The chemical composition of magma strongly influences this process. Magma rich in silica tends to be thicker and more resistant to flow. This resistance makes it harder for gas bubbles to escape. As a result, pressure can build rapidly within the magma. When that pressure is finally released, the eruption can be violent and explosive. In contrast, magma with lower silica content is more fluid. Gases can escape more easily, reducing pressure buildup. When this type of magma erupts, it often produces gentle lava flows rather than explosive events. The difference between a flowing lava field and a catastrophic eruption often begins with this invisible chemical balance underground. When magma finally reaches the surface, it is then called lava. This change in name marks a dramatic shift in conditions. Pressure drops suddenly. Gases escape rapidly. Heat begins to dissipate into the surrounding air or water. Lava begins cooling almost immediately, even as it continues to move. The cooling process creates a wide variety of surface textures. Some lava flows cool smoothly, forming rope-like patterns. Others break into jagged blocks as they advance. These textures are physical records of temperature, viscosity, and movement at the moment of eruption. Geologists can read these patterns much like a history written in stone. It is also important to understand that magma does not always become lava. In many volcanic systems, magma rises partway through the crust and then stalls. It cools slowly underground, crystallizing into solid rock without ever erupting. These solidified bodies remain hidden beneath the surface, evidence of volcanic activity that never reached public awareness. This means that visible eruptions represent only a small fraction of volcanic activity on Earth. Much of the planet's internal heat is released quietly, without lava fountains or ash clouds. Volcanoes are active even when nothing appears to be happening. The journey from magma to lava is shaped by countless variables: pressure gradients, gas content, chemistry, and crustal structure. No two journeys are identical. This is why volcanoes vary so widely in behavior, even when they appear similar from the outside. Understanding magma and lava as stages of the same process removes much of the mystery surrounding volcanic eruptions. What happens at the surface is simply the final expression of changes that began deep underground, long before any eruption became visible. Magma does not appear randomly inside the Earth. It forms only when specific physical conditions come together. These conditions involve heat, pressure, and the presence of certain substances that change how rock behaves. Understanding where magma comes from means understanding how solid rock can begin to melt without turning the entire mantle into a liquid. Deep inside the Earth, temperature increases steadily with depth. However, high temperature alone is not enough to create magma. Pressure also increases with depth, and this pressure raises the melting point of rock. As a result, much of the mantle remains solid even though it is extremely hot. This balance between heat and pressure is what keeps the mantle stable most of the time. Magma forms when this balance is disturbed. One way this happens is through decompression. When hot mantle rock slowly rises toward the surface, pressure decreases faster than temperature does. Even though the rock is not getting hotter, the drop in pressure allows a portion of it to melt. This type of melting is common beneath mid-ocean ridges, where tectonic plates are moving apart and mantle material is rising to fill the gap. Another pathway to magma formation involves water and other volatile substances. In certain regions, especially where one tectonic plate is pushed beneath another, water trapped in the descending plate is released into the surrounding mantle. This water lowers the melting point of the rock it comes into contact with. The rock begins to partially melt even though temperature and pressure have not changed dramatically. This process is responsible for many of the explosive volcanoes found along subduction zones. Partial melting is a crucial concept. Rock does not need to melt completely to generate magma. Even a small percentage of melt is enough. When melting begins, the liquid portion separates from the solid minerals because it is less dense. This separation creates magma that can migrate independently of the surrounding solid rock. The composition of the original rock also matters. Different mantle rocks melt at different temperatures and produce magmas with different chemical properties. These differences influence how viscous the magma will be, how much gas it can hold, and how it will behave if it reaches the surface. Once magma forms, it begins a slow upward journey driven by buoyancy. But this movement is neither straight nor continuous. Magma may rise a short distance and then stall, cooling and crystallizing before melting again if conditions change. It may mix with other magma batches, altering its composition over time. These interactions help explain why eruptions from the same volcano can look very different from one another. It is also important to recognize that magma generation is not evenly distributed across the planet. It is concentrated in specific geological settings, along plate boundaries, above mantle hotspots, and beneath regions where the crust is thinning. These settings provide the conditions necessary for partial melting to occur repeatedly. The formation of magma is therefore not a violent or sudden event. It is a gradual response to long-term changes in pressure, temperature, and composition inside the Earth. By the time magma is capable of feeding a volcano, it has already undergone a complex history of formation, movement, and transformation. This deep origin story explains why volcanoes are predictable in location, even if their timing is uncertain. The Earth's interior follows physical rules, and magma forms only where those rules allow it. As magma forms and begins its slow movement upward, it does not usually travel directly to the surface. Instead, it often pauses within the Earth's crust. These pauses are not accidents. They are a natural consequence of how magma interacts with the surrounding rock. The places where magma temporarily collects are commonly called magma chambers, though the name can be misleading. A magma chamber is not an empty underground cave filled with glowing liquid. In reality, it is a complex zone where molten material, solid rock, and partially melted crystals coexist. Some regions within a chamber may be mostly solid, while others contain pockets of melt. This structure is constantly changing as magma cools, reheats, and mixes with new material arriving from below. Magma tends to stall in the crust because the crust itself is layered and uneven. As magma rises, it encounters rocks of different densities, temperatures, and strengths. When the upward force driving magma movement balances with resistance from surrounding rock, magma slows down or stops. Over time, repeated intrusions of magma can enlarge these storage zones, making them more stable reservoirs. Inside a magma chamber, important changes occur. Temperature differences cause some minerals to crystallize while others remain molten. Heavier crystals may sink, while lighter components rise. This process, known as magmatic differentiation, gradually alters the chemical composition of the magma. As a result, magma stored in a chamber can behave very differently from the magma that originally entered it. Gas behavior inside magma chambers is equally important. Gases released from deeper magma may accumulate in the upper parts of the chamber, increasing internal pressure. If new magma continues to arrive from below, pressure can build steadily over time. This pressure does not always lead to an eruption. Sometimes it is released slowly through cracks, allowing magma to cool and solidify without reaching the surface. Magma chambers also explain why volcanoes can erupt repeatedly over long periods. A chamber can remain partially molten for thousands of years, fed intermittently by new magma. Each eruption draws from this evolving reservoir, which is why eruptions from the same volcano can vary so widely in style and intensity. It is important to understand that magma chambers are rarely stable or symmetrical. They can shift position, split into multiple pockets, or migrate upward as the crust deforms. In some cases, magma spreads laterally instead of rising vertically, creating extensive underground intrusions that never erupt at all. Modern science has revealed magma chambers not by direct observation, but by indirect evidence. Seismic waves slow down when they pass through partially molten regions. Ground deformation shows where pressure is increasing below the surface. Changes in gas emissions can indicate movement of magma at depth. Together, these signals allow scientists to infer the presence and behavior of magma chambers without ever seeing them. The existence of magma chambers changes how eruptions are understood. An eruption is not the sudden appearance of magma from deep within the earth. It is the release of material that has often been stored, altered, and pressurized over long periods of time. What happens at the surface is only the final stage of a much longer underground process. By recognizing magma chambers as dynamic systems rather than static pools, volcanoes begin to look less like unpredictable threats and more like complex geological machines, responding slowly to changes deep within the planet. Magma is not just molten rock. It is a pressurized system carrying dissolved gases that behave very differently depending on depth. To understand why eruptions happen at all, and why they happen the way they do, we need to understand how pressure and gas interact inside magma as it moves upward. Deep underground, pressure is immense. At those depths, gases such as water vapor, carbon dioxide, and sulfur compounds remain dissolved within the magma. They are present, but they are invisible, compressed by the weight of the rock above. In this state, magma can exist quietly for long periods without any sign of instability. As magma rises, the surrounding pressure begins to drop. This change does not happen suddenly, but even gradual pressure loss has powerful effects. Gases that were once dissolved start to separate from the molten rock. Tiny bubbles form, similar to what happens when a sealed bottle is opened and dissolved gas escapes. What happens next depends on whether those bubbles can escape. If magma is fluid and pathways exist, gases can rise through it and release pressure gradually. In this situation, magma may continue moving upward without dramatic consequences, eventually producing gentle lava flows. If magma is thick and resistant to flow, gas bubbles struggle to escape. They become trapped, growing larger as more gas comes out of solution. Pressure builds within the magma, not because new material is added, but because expanding gas needs space. This internal pressure is one of the primary drivers of explosive eruptions. The breaking point occurs when the pressure inside the magma exceeds the strength of the surrounding rock. Cracks begin to propagate upward, sometimes rapidly. Once a fracture reaches the surface, pressure is released violently, allowing gas to expand suddenly. This expansion fragments the magma into ash and propels material upward with great force. Importantly, pressure buildup does not guarantee an eruption. Magma chambers can release pressure slowly through small fractures, allowing gas to escape without magma reaching the surface. In other cases, pressure may fluctuate for years or decades before crossing a critical threshold. This explains why volcanoes can show warning signs long before erupting. Small earthquakes, ground swelling, and increased gas emissions are all surface expressions of pressure changes happening underground. These signals reflect movement and adjustment within the magma system, not a countdown to a guaranteed eruption. Pressure also explains why eruptions vary so dramatically. Two volcanoes may contain similar magma, yet behave very differently depending on how pressure is released. The eruption style is not a matter of chance. It is the outcome of gas behavior interacting with magma properties and crustal structure. Understanding pressure and gas removes much of the mystery surrounding volcanic violence. Explosive eruptions are not sudden acts of chaos. They are mechanical failures, moments when a pressurized system exceeds its limits and releases energy according to physical laws. Why some volcanoes explode while others flow? Not all volcanoes behave the same way. Some release lava quietly, allowing molten rock to spread slowly across the ground. Others erupt violently, sending ash and gas high into the atmosphere. This contrast is not random, and it is not determined by the size of the volcano. It is controlled by a small set of physical properties inside the magma itself. One of the most important of these properties is viscosity, a measure of how easily a fluid flows. Low-viscosity magma moves easily, like warm syrup. High-viscosity magma resists motion, more like thick paste. This single difference shapes the entire personality of a volcano. Viscosity is largely controlled by chemical composition, especially the amount of silica in the magma. Silica forms complex molecular structures that make molten rock more resistant to flow. Magma rich in silica is thick and sticky. Magma low in silica is more fluid and mobile. This difference has immediate consequences for gas behavior. In fluid magma, gas bubbles can rise, merge, and escape gradually. Pressure is released steadily, often without any explosive outcome. When such magma reaches the surface, it tends to produce long, flowing lava streams that reshape landscapes without sudden violence. In thick, silica-rich magma, gas bubbles struggle to move. They become trapped within the melt, accumulating pressure over time. As more gas comes out of solution during ascent, the internal pressure increases. The magma itself resists deformation, so instead of flowing, it stores energy. When this trapped pressure exceeds the strength of the surrounding rock, the release is abrupt. The magma shatters into fragments, producing ash rather than smooth lava. What appears to be an explosion is actually a rapid mechanical failure driven by expanding gas. Temperature also plays a role. Hotter magma flows more easily than cooler magma, even if their compositions are similar. As magma cools during storage or ascent, viscosity increases. This means the same volcano can produce different eruption styles at different times, depending on how long magma has been stored and how much it has cooled. Crystals suspended in magma further increase resistance to flow. As magma sits in storage zones, crystals grow. These solid particles interfere with movement, raising viscosity and making gas escape more difficult. Over time, a magma body can evolve from relatively fluid to highly explosive without any change in its source. This explains why volcanoes are not permanently gentle or permanently violent. Their behavior reflects the current state of their magma, not a fixed identity. The same volcanic system can alternate between quiet lava flows and explosive eruptions across its lifespan. Understanding this balance between viscosity, gas, temperature, and crystal content reveals a deeper truth. Explosive eruptions are not mysterious outbursts. They are predictable outcomes when thick magma traps gas beyond its breaking point. Gentle eruptions are not safer by chance. They are the natural result of magma that allows pressure to escape. Once this principle is clear, the wide diversity of volcanic behavior begins to make sense. What happens at the surface is a direct expression of invisible properties developing deep underground, governed by chemistry and physics rather than randomness. Water plays a quiet but powerful role in volcanism. It does not create magma on its own, and it does not erupt like lava, yet it strongly influences when magma forms, how it moves, and how violently it erupts. Without water, many of the world's most explosive volcanoes would behave very differently. To understand this role, it helps to think about how rocks melt. Deep inside the Earth, high pressure keeps most rocks solid even at very high temperatures. Adding water to these rocks changes that balance. Water lowers the temperature at which rock begins to melt. This means that magma can form in regions that would otherwise remain solid. One of the most important places where this happens is at subduction zones. These are regions where one tectonic plate sinks beneath another. The descending plate carries water with it, trapped inside minerals and sediments that formed at the surface. As the plate sinks deeper, heat and pressure release this water into the surrounding mantle. When water enters the hot mantle above a subducting plate, it triggers partial melting. The rock does not need to become hotter. The presence of water alone is enough to allow melt to form. This process explains why chains of volcanoes appear parallel to deep ocean trenches around the world. The volcanoes are not sitting directly above the sinking plate by accident. They are responding to water released at specific depths. Water also affects magma after it forms. Dissolved water becomes part of the gas content within magma. At depth, this water remains dissolved due to high pressure. As magma rises and pressure decreases, water comes out of solution as vapor. This expansion contributes significantly to internal pressure. Compared to carbon dioxide, water vapor is especially effective at driving explosive eruptions. It expands rapidly when pressure drops, increasing the energy released during an eruption. Magma rich in water is therefore more likely to fragment into ash rather than flow smoothly as lava. Water can also interact with magma closer to the surface. When rising magma encounters groundwater, lakes, or seawater, the results can be dramatic. The sudden conversion of water to steam produces powerful explosions, even when the magma itself is not particularly gas-rich. These are known as phreatic or phreatomagmatic eruptions. In such cases, the eruption is driven not by magma chemistry, but by physical interaction between heat and water. Rock is shattered, ash is produced, and steam carries material upward. These eruptions can occur with little warning because they depend on surface water conditions rather than deep magma movement. Water influences not only eruption style, but also long-term volcanic behavior. Magma that contains significant water tends to cool and crystallize differently in storage zones. This affects viscosity, gas retention, and the likelihood of pressure buildup over time. In this way, water shapes both immediate eruptions and future ones. Even after an eruption, water continues to play a role. Volcanic ash interacts with moisture in the atmosphere, influencing cloud formation and rainfall patterns. Water-driven erosion reshapes volcanic landscapes rapidly, carving valleys and transporting sediments away from newly formed land. Despite its importance, water's role in volcanism is often overlooked because it is invisible deep underground. Yet many of the world's most powerful volcanoes owe their existence and behavior to the presence of water carried deep into the earth by moving plates. Understanding this relationship highlights an important pattern. Volcanoes are not driven by a single factor. Heat, pressure, chemistry, and fluids work together. Water acts as a catalyst within this system, quietly increasing the potential for change without ever appearing as the main actor. Volcanoes do not appear randomly across the Earth's surface. Their locations follow clear patterns, shaped by the slow movement of tectonic plates and by deep sources of heat rising from within the mantle. Once magma formation and pressure behavior are understood, the geography of volcanoes begins to make sense. The Earth's outer shell is broken into large pieces called tectonic plates. These plates move slowly, only a few centimeters per year, but over millions of years their motion reshapes the planet. Where these plates interact, conditions often become favorable for magma generation and volcanic activity. One major setting for volcanoes is where plates move apart, known as divergent boundaries. At these locations, the crust stretches and thins. As plates separate, hot mantle material rises to fill the gap. Pressure decreases as this material rises, allowing partial melting to occur. Magma forms and moves upward, creating new crust as it cools. This process happens continuously along mid-ocean ridges, where most of Earth's volcanic activity takes place, hidden beneath the sea. Another important setting is where plates collide, particularly where one plate sinks beneath another. These are subduction zones. As the descending plate moves deeper into the mantle, it releases water into the surrounding rock. This water lowers the melting point of the mantle, generating magma above the sinking plate. The magma rises through the crust, feeding chains of volcanoes that often form curved arcs along continental margins or island chains. Subduction zone volcanoes are responsible for many of the world's most explosive eruptions. Their magma is often rich in water and silica, increasing viscosity and gas retention. These conditions make pressure build up more likely, leading to violent releases of energy when eruptions occur. Not all volcanoes are tied directly to plate boundaries. Some form far from the edges of plates, above regions known as hotspots. Hotspots are thought to be caused by columns of hot material rising from deep within the mantle. These columns, sometimes called mantle plumes, remain relatively fixed while tectonic plates move over them. As a plate drifts across a hotspot, magma rises repeatedly through the crust, forming a chain of volcanoes. Over time, older volcanoes move away from the heat source and become inactive, while new ones form above it. This creates linear chains that record the motion of tectonic plates across the planet. Hotspot volcanoes often produce fluid magma with low silica content, leading to gentle eruptions and broad volcanic structures. However, this is not always the case. The interaction between plume material and crustal composition can still produce varied eruption styles. There are also volcanic regions linked to crustal thinning rather than clear plate boundaries. In these areas, the crust is stretched by tectonic forces, creating fractures that allow magma to rise. These volcanoes may not align neatly along a single boundary, but their existence still reflects deeper structural changes in the lithosphere. Understanding where volcanoes form reveals an important truth. Volcanism is a surface expression of plate motion and mantle dynamics. The Earth's surface is constantly being reshaped by forces operating far below, following patterns that can be mapped and studied. Once these patterns are recognized, volcanic regions around the world begin to connect into a global system. Each eruption, no matter how isolated it appears, is part of a larger network of heat transfer and material circulation within the planet. When people imagine a volcano, they often picture a tall, steep cone with lava flowing down its sides. In reality, volcanoes come in many shapes and sizes. These shapes are not cosmetic. Each one is a physical record of how magma behaved during repeated eruptions over long periods of time. One common volcanic form is the shield volcano. These volcanoes are wide, gently sloping, and low compared to their size. They are built almost entirely by fluid lava that flows easily and travels far before cooling. Each eruption adds a thin layer, and over time these layers spread outward rather than upward. The result is a broad structure that resembles a shield resting on the ground. Shield volcanoes are usually associated with low-viscosity magma. Because gases can escape easily, eruptions tend to be calm and persistent rather than violent. Lava flows may continue for long durations, slowly reshaping the landscape without producing large ash clouds. Much of the surface area of some islands and continental regions has been formed this way. In contrast, stratovolcanoes, also known as composite volcanoes, are tall and steep-sided. They are built from alternating layers of lava flows, ash, and fragmented volcanic material. Each layer tells a different story of eruption style. Some eruptions produce flowing lava, while others explode, depositing ash and debris. The steep shape of stratovolcanoes reflects the behavior of their magma. Thick, viscous magma does not travel far once it reaches the surface. Instead, it piles up near the vent. Ash and fragmented material accumulate rapidly, building height rather than width. Over time, repeated eruptions create the classic conical shape. There are also cinder cones, which are smaller and simpler structures. These form when gas-rich magma is expelled into the air and cools into small fragments before landing around the vent. The fragments accumulate quickly, creating steep-sided cones. Cinder cones often form in clusters and may exist alongside larger volcanic systems. Another important volcanic structure is the caldera. Calderas are not built by accumulation. They form when a large volume of magma is removed from beneath the surface during a major eruption. Without support, the ground above collapses inward, creating a broad depression. Calderas can be mistaken for craters, but they are much larger and represent a different process entirely. Some volcanoes change shape over time. A volcano that begins with fluid lava flows may later erupt more viscous magma, altering its structure. Others may partially collapse due to erosion, landslides, or internal weakening. The shape of a volcano is therefore not fixed. It evolves as the internal system changes. These different forms show that volcanoes are not simply mountains with lava inside. They are geological records. Their shapes preserve information about magma composition, eruption frequency, gas behavior, and interaction with the surrounding environment. By reading these shapes carefully, scientists can infer how a volcano has behaved in the past and how it might behave in the future. The surface form becomes a visible map of invisible processes that operated beneath the Earth for thousands or even millions of years. When a volcano erupts, what reaches the surface is often described simply as lava or ash. In reality, volcanic eruptions produce a wide range of materials, each formed by different physical processes. These materials are not random byproducts. They reflect how magma behaved at the moment pressure was released. Lava is molten rock that flows across the surface before cooling and solidifying. Its movement depends on temperature, viscosity, slope, and the rate at which it loses heat. Some lava remains hot and fluid long enough to travel great distances. Other lava cools quickly, thickening and slowing until it piles up near the vent. Once solidified, lava becomes igneous rock, permanently recording the conditions under which it cooled. Volcanic ash is often misunderstood. It is not burned material, and it is not the result of fire. Ash consists of tiny fragments of rock, glass, and minerals created when magma is shattered by expanding gas. These particles are sharp, abrasive, and extremely fine. Because of their size, ash can remain suspended in the atmosphere and travel far from the eruption site. Ash plays a major role in volcanic hazards, but it also contributes to long-term environmental change. Over time, ash breaks down into nutrient-rich soils that support agriculture in many volcanic regions. What begins as destructive fallout can eventually become the foundation for fertile land. Larger fragments produced during eruptions are called tephra. These include volcanic bombs and blocks, which are thrown from the volcano during explosive activity. Their size and distribution provide clues about eruption energy and gas pressure. Heavier fragments fall close to the vent, while lighter ones travel farther. Some eruptions produce pyroclastic flows, which are fast-moving mixtures of hot gas, ash, and rock fragments. These flows move along the ground rather than rising into the sky. Their behavior is controlled by gravity and density, allowing them to travel rapidly down slopes and through valleys. Pyroclastic flows form when eruption columns collapse or when magma fragments violently at the surface. Volcanoes also release gases in large quantities. Water vapor is usually the most abundant, followed by carbon dioxide and sulfur-containing gases. These gases influence eruption dynamics, air quality, and climate. Even when no eruption is visible, gas release can indicate magma movement below the surface. Over time, the materials produced by volcanoes accumulate and interact with the environment. Lava alters landscapes, ash enriches soils, and gases modify atmospheric chemistry. Each eruption adds another layer to the geological and ecological history of a region. By examining what volcanoes produce, scientists can reconstruct how an eruption unfolded, even long after it has ended. The rocks left behind are not just remnants of destruction. They are records of physical processes acting under extreme conditions. When a volcano erupts explosively, its influence does not stop at the ground. Some of the most important effects of volcanism happen far above the surface, in the atmosphere. This begins with volcanic ash, a material so fine and light that it can travel far beyond the volcano itself. Volcanic ash is created when magma is shattered by rapidly expanding gas. Instead of flowing as lava, the magma breaks into countless tiny fragments. These fragments are small enough to be carried upward by rising hot gases, forming a vertical column above the volcano. The height of this column depends on eruption energy, gas content, and atmospheric conditions. As the column rises, it cools and spreads outward, forming an ash cloud. Wind patterns then carry this cloud across regions, countries, and sometimes entire continents. Unlike lava, which is limited by gravity and terrain, ash is controlled by air currents. This allows a single eruption to affect areas far removed from the source. Ash in the atmosphere has immediate physical effects. Fine particles can reduce visibility, damage machinery, and disrupt air travel. More importantly, ash particles interact with sunlight. They scatter and absorb radiation, changing how energy moves through the atmosphere. This can lead to short-term cooling at the surface, even far from the volcano. Volcanic ash also carries gases upward, particularly sulfur-containing compounds. When these gases reach the upper atmosphere, they can form tiny droplets that remain suspended for long periods. These droplets reflect sunlight back into space, reducing the amount of energy that reaches the Earth's surface. The result is a measurable cooling effect that can last months or even years. The extent of this impact depends on how much material reaches high altitudes. Small eruptions may produce local ash fall without significant atmospheric consequences. Larger eruptions can inject material into the stratosphere, where it spreads globally and persists much longer. Ash eventually settles back to the ground, but its effects do not end there. When it falls, it can alter soil chemistry, damage crops temporarily, and affect water supplies. Over time, however, weathering breaks ash down into minerals that enrich the soil. This long-term benefit contrasts sharply with the short-term disruption. Atmospheric ash also provides scientists with valuable information. By studying ash layers preserved in ice cores, lake sediments, and ocean floors, researchers can reconstruct past eruptions and their environmental effects. These records help connect volcanic activity with climate variations in Earth's history. Understanding how volcanoes interact with the atmosphere reveals a broader truth. Volcanic eruptions are not confined to the land. They link Earth's interior to its climate system, influencing air, light, and temperature far beyond the point of eruption. Volcanoes are often thought of as local geological events, but some eruptions have consequences that extend far beyond the region where they occur. When volcanic material reaches high enough into the atmosphere, it can influence climate on a global scale. These changes do not come from lava or ash alone, but from the interaction between volcanic gases and the atmosphere. One of the most important volcanic gases affecting climate is sulfur dioxide. During large explosive eruptions, sulfur dioxide is released in enormous quantities and carried high into the atmosphere along with ash. Once there, it reacts with water vapor to form tiny droplets of sulfuric acid. These droplets spread around the planet, forming a thin veil that reflects incoming sunlight. This reflection reduces the amount of solar energy reaching Earth's surface. The result is a cooling effect, often small in daily terms but significant when averaged across the globe. Temperatures may drop slightly, growing seasons can shorten, and weather patterns can shift. These effects are temporary, but they can last long enough to be felt by ecosystems and human societies. Volcanic cooling is not uniform. Some regions experience stronger temperature changes than others, depending on atmospheric circulation. Changes in rainfall patterns can occur, with some areas becoming drier while others receive more precipitation. These shifts show how closely linked volcanic activity is to atmospheric dynamics. Unlike long-term climate change driven by greenhouse gases, volcanic climate effects are short-lived. The particles and droplets responsible eventually settle out of the atmosphere. Within a few years, the climate system usually returns to its previous state. However, the temporary disruption can still leave lasting marks, especially if it coincides with sensitive periods for agriculture or ecosystems. Volcanoes can also influence climate indirectly. Ash falling on ice and snow can darken surfaces, causing them to absorb more sunlight and melt faster. Changes in vegetation caused by ash fall can alter how land reflects heat. These feedbacks demonstrate that volcanic impacts are not limited to the moment of eruption. Scientific understanding of volcanic climate influence has grown through careful study of past events. Ice cores, tree rings, and sediment layers preserve signals of cooling linked to known eruptions. By comparing these records, Scientists can estimate how much material entered the atmosphere and how strongly it affected global temperatures. This connection between volcanoes and climate highlights a larger principle. Earth systems are deeply interconnected. Activity deep within the planet can alter conditions in the atmosphere, affecting weather, ecosystems, and even human history. Volcanoes serve as reminders that climate is shaped not only by surface processes, but also by forces rising from far below. After understanding how magma forms, how pressure builds, and how volcanic material reaches the atmosphere, it becomes possible to look at historical eruptions in a different way. Instead of seeing them as isolated disasters, they can be examined as real-world outcomes of the processes already described. One of the clearest examples of this is the eruption of Mount Vesuvius in the 1st century. Vesuvius sits near the coast of southern Italy, in a region shaped by complex plate interactions. Beneath it, magma formed in a water-rich environment linked to subduction processes. This magma was relatively viscous and capable of trapping large amounts of gas, a combination already known to favor explosive behavior. For many years before the eruption, Vesuvius appeared quiet. The mountain was present, but its deeper system remained hidden. Magma had accumulated in storage regions beneath the surface, evolving chemically and increasing in gas content. Pressure built gradually, without obvious surface eruptions to release it. When the eruption finally began, it did not start with a massive explosion. Initial activity released ash and gas, forming a tall eruption column. As pressure continued to rise, the column grew unstable. Eventually, parts of it collapsed, sending fast-moving currents of hot gas, ash, and rock fragments down the slopes. These currents, now understood as pyroclastic flows, moved too quickly and were too hot for escape. They traveled along the terrain, following valleys and low ground, reaching nearby settlements within minutes. Among these settlements was Pompeii, a city that would later become one of the most important archaeological records of volcanic behavior. What makes this eruption scientifically valuable is not just its scale, but its clarity. The sequence of events matches the physical principles already discussed. Gas-rich magma rose, pressure exceeded rock strength, fragmentation occurred, and gravity-driven flows followed. Nothing about the eruption violated the rules of physics. It followed them precisely. The preservation of buildings, objects, and human remains beneath volcanic deposits has allowed scientists to reconstruct the eruption in detail. Layers of ash reveal changes in eruption intensity. Deposits of fragmented rock show where eruption columns collapsed. Even the direction and thickness of materials provide information about wind patterns and eruption duration. This eruption also highlights an important misconception. The greatest danger did not come from lava flows. Lava played a minor role. The most destructive forces were ash, gas, and rapidly moving currents created by pressure release and collapse within the eruption column. Vesuvius demonstrates how quickly a volcanic system can transition from quiet storage to catastrophic release once critical thresholds are crossed. It also shows why understanding magma chemistry, gas behavior, and pressure is essential for interpreting volcanic risk. By viewing this eruption through a scientific lens, it becomes clear that history and geology are deeply connected. Historical eruptions are not separate from theory. They are confirmations of it, recorded in real landscapes and preserved by chance. Some eruptions are remembered not because of where they occurred, but because of how far their effects reached. The eruption of Krakatoa in the late 19th century is one such case. It offers a clear window into the physics of volcanic energy, how pressure is released, how shock waves travel, and how an eruption can briefly interact with the entire atmosphere. Krakatoa was located in a narrow strait between large landmasses, with seawater surrounding much of the volcanic structure. Beneath it, magma had accumulated and evolved over time, storing gas under high pressure. When the eruption sequence intensified, multiple explosions occurred in quick succession. Each release removed support from the volcanic structure, allowing seawater to rush into contact with hot magma. This interaction between water and magma amplified the violence of the eruption. Rapid conversion of water to steam added energy to an already pressurized system. The result was not a single blast, but a series of powerful explosions that progressively dismantled the volcano itself. One of the most striking features of the Krakatoa eruption was the generation of pressure waves. These waves moved outward through the atmosphere, traveling vast distances. Instruments around the world recorded sudden changes in air pressure as the waves passed by. The atmosphere responded like a stretched membrane that had been sharply struck. The eruption column rose high into the sky, injecting ash and gas into upper atmospheric layers. The collapse of parts of this column sent material outward in all directions. The energy released was sufficient to reshape coastlines, generate massive ocean waves, and alter local geography almost instantly. From a scientific perspective, Krakatoa illustrates how volcanic energy scales nonlinearly. Small increases in pressure or gas content do not lead to small increases in eruption strength. Once a system crosses certain thresholds, the response can grow rapidly. The physics governing this behavior is the same as that discussed earlier: gas expansion, pressure release, and mechanical failure, but operating at an extreme scale. The atmospheric effects of the eruption were also notable. Fine particles and gases spread globally, altering how sunlight interacted with the atmosphere. Unusual optical effects were reported for months afterward, as suspended material scattered light in unfamiliar ways. These observations later helped scientists understand how volcanic aerosols influence climate and atmospheric circulation. Krakatoa's eruption demonstrates that volcanoes can briefly become planetary-scale events. For a short time, the boundary between Earth's surface and its atmosphere becomes an active interface, transferring energy upward and outward. What makes this case especially valuable is that it connects multiple concepts at once. Magma chemistry, water interaction, pressure dynamics, atmospheric physics, and global circulation all intersect in a single event. Rather than being an outlier, Krakatoa represents what happens when known processes operate under rare but possible conditions. Seen this way, the eruption is not a mystery or an anomaly. It is a reminder that volcanic systems can store energy quietly for long periods, then release it according to physical laws that scale with the size and configuration of the system. Despite the dangers they present, volcanoes have attracted human settlement for thousands of years. This is not because people underestimate the risks, but because volcanic regions also offer powerful advantages. Understanding why humans choose to live near volcanoes reveals how geological processes shape societies, economies, and long-term decision-making. One of the strongest attractions is fertile soil. Volcanic ash contains minerals that, once broken down by weathering, enrich the ground with nutrients. Over time, these soils become highly productive, supporting agriculture that can sustain dense populations. Many historically important farming regions exist because of past volcanic activity. Volcanoes also influence water resources. The fractured rock around volcanic systems often stores groundwater efficiently. Springs and aquifers form where water moves through porous volcanic layers. These water sources can be reliable even in otherwise dry regions, making settlement more sustainable. Beyond agriculture and water, Volcanic regions often provide raw materials. Volcanic rock has been used for tools, construction, and trade. In more recent times, volcanic heat has been harnessed as a source of geothermal energy, providing electricity and heating with relatively low emissions. This turns a geological hazard into a long-term resource. At the same time, living near volcanoes requires constant negotiation with risk. Volcanic hazards are not limited to eruptions. Ash fall, gas release, landslides, and mud flows can occur even when a volcano appears quiet. Communities in these regions develop local knowledge, traditions, and infrastructure designed to reduce vulnerability. Modern societies rely increasingly on scientific monitoring to manage these risks. Early warning systems, hazard maps, and evacuation plans are informed by geological data rather than superstition or guesswork. Even so, decisions are rarely simple. Evacuations disrupt lives and economies, while false alarms can reduce trust over time. This balance between benefit and danger explains why volcanic regions remain populated. The choice is not irrational. It reflects a calculation shaped by geography, history, and opportunity. Volcanoes provide resources that are difficult to replace elsewhere, while their risks, though serious, are intermittent. Looking at human interaction with volcanoes highlights an important theme. Natural hazards are not purely natural problems. They become human problems when societies choose how and where to live. Volcanoes force these choices into the open, revealing how deeply human life is intertwined with Earth's internal processes. Volcanoes rarely erupt without internal changes first. Long before lava reaches the surface or ash enters the sky, the Earth begins to send subtle signals. Modern volcanic science is built around learning how to detect, interpret, and combine these signals to understand what is happening underground. One of the most important tools in volcanic monitoring is the measurement of seismic activity. As magma moves through rock, it causes small fractures and vibrations. These vibrations travel as seismic waves and can be detected by sensitive instruments called seismometers. Unlike earthquakes caused by tectonic plate movement, volcanic earthquakes often follow distinct patterns. Their depth, frequency, and rhythm provide clues about magma migration and pressure changes. Ground movement is another key signal. When magma accumulates beneath a volcano, it can cause the surface to slowly rise or tilt. This deformation may be subtle, sometimes only a few millimeters, but it can be measured precisely using GPS instruments and satellite-based radar systems. Inflation suggests that magma or gas is entering a storage zone, while deflation can indicate magma withdrawal or pressure release. Volcanic gases also provide valuable information. As magma rises, gases escape through cracks and vents, sometimes long before an eruption occurs. By measuring changes in gas composition and emission rates, scientists can infer what is happening below the surface. An increase in certain gases may signal that fresh magma is moving upward, while changes in gas ratios can suggest shifts in pressure or temperature. Thermal monitoring adds another layer of insight. Heat escaping from the ground, vents, or crater lakes can indicate changes in magma depth or activity. Infrared sensors mounted on satellites or aircraft allow scientists to track temperature variations over large areas, even in remote or dangerous locations. No single signal provides a complete picture. Volcanic systems are complex, and each volcano behaves differently. This is why modern monitoring relies on combining multiple data streams. Seismic patterns, ground deformation, gas emissions, and thermal changes are analyzed together to build models of what is happening underground. Despite these advances, volcanic prediction remains uncertain. Monitoring can identify increasing risk, but it cannot determine the exact timing, size, or style of an eruption. Volcanoes respond to internal conditions that evolve in nonlinear ways. Small changes can stabilize a system or push it toward failure. What monitoring does provide is time. Even hours or days of warning can reduce loss of life and allow communities to prepare. The goal is not perfect prediction, but informed decision-making based on the best available evidence. Volcano monitoring represents a shift in how humans interact with geological hazards. Instead of reacting after events occur, science allows societies to observe processes in real time, turning the invisible dynamics of the Earth into measurable signals. Not all volcanoes fit the familiar image of a mountain with a central crater. Some of the most powerful volcanic systems on Earth leave behind no tall cone at all. These are known as supervolcanoes, and their defining feature is not shape, but scale. They are capable of eruptions far larger than those produced by typical volcanic systems, driven by processes that operate over much longer timescales. A supervolcano is identified by the size of the eruption it can produce, not by how often it erupts. These systems store enormous volumes of magma beneath the surface, spread across wide regions rather than confined to a narrow chamber. Over thousands to hundreds of thousands of years, magma accumulates, cools partially, crystallizes, and evolves chemically. Gas becomes trapped within this large, slowly changing body. Unlike smaller volcanoes, supervolcanoes often show little surface activity for long periods. Their magma systems are deep, broad, and stable for most of their existence. Pressure does not build quickly. Instead, it accumulates gradually as magma continues to enter the system and gases remain trapped. This long buildup is what allows such systems to reach extreme potential energy. When failure occurs, it is not through a narrow vent. Instead, large sections of the ground collapse inward as magma is released. The result is a massive caldera, sometimes tens of kilometers wide. These collapses mark eruptions that release thousands of times more material than typical volcanic events. The effects of such eruptions extend far beyond the immediate region. Ash can blanket continents. Fine particles and gases injected into the upper atmosphere can persist for years, altering global temperatures and disrupting climate patterns. These impacts are not instantaneous disasters, but prolonged environmental changes that affect ecosystems worldwide. Despite their scale, supervolcanoes follow the same physical principles discussed earlier. Gas expansion, pressure release, magma viscosity, and mechanical failure still govern behavior. The difference lies in the size of the system and the duration of buildup. A supervolcano is not governed by new rules, but by familiar rules operating over much larger volumes and longer times. Importantly, supervolcanoes are extremely rare in human timescales. Their eruptions are separated by tens of thousands of years or more. This rarity often leads to misunderstanding, with either exaggerated fear or complete dismissal. In reality, these systems are best understood as long-term geological processes rather than imminent threats. Modern monitoring of supervolcano regions focuses on slow changes, subtle ground deformation, deep seismic patterns, and gas emissions over wide areas. These signals are interpreted cautiously because supervolcano systems can remain restless without progressing toward eruption. Supervolcanoes remind us that Earth's most dramatic changes often unfold slowly. Their power comes not from sudden instability, but from patience, long periods of quiet accumulation that, under rare conditions, reach a breaking point. Once eruptions range from gentle lava flows to continent-scale ash clouds, a natural question appears. How do scientists compare one eruption to another in a meaningful way? Size alone is not enough. Height, duration, volume, and energy all matter. To bring order to this complexity, volcanology uses structured measurement systems that focus on what an eruption actually releases into the environment. The most widely used framework is the Volcanic Explosivity Index, often shortened to VEI. Rather than ranking eruptions by drama or destruction, this scale focuses on the volume of material expelled and the height of the eruption column. Each step on the scale represents a large increase in erupted material, not a small one. This means the difference between neighboring categories is substantial. Lower VEI eruptions involve small volumes of lava or ash and tend to affect only local areas. These eruptions may continue for long periods but release energy gradually. Higher VEI eruptions involve rapid release of enormous volumes of fragmented material, often accompanied by tall ash columns that reach the upper atmosphere. These events are rare, but capable of producing global effects. What makes the VEI useful is not just classification, but context. Two eruptions that look visually similar can differ greatly in scale once volume and column height are measured. Conversely, an eruption that appears modest at the surface may inject material high enough to influence climate systems. However, the VEI does not capture everything. It does not directly measure lava flow extent, gas output, or eruption duration. Some eruptions release large volumes of lava quietly over time and have low VEI values despite major landscape change. Others are brief but violently explosive. This shows that no single number can fully describe volcanic behavior. To address this, scientists combine VEI with additional data: magma composition, gas chemistry, eruption duration, and deposit thickness. By examining ash layers preserved in sediments and ice cores, researchers can estimate past eruption sizes even when written records do not exist. These reconstructions allow modern eruptions to be placed within a deep historical framework. Measuring eruption power also helps explain why some events are remembered for centuries while others fade quickly. An eruption's impact depends not only on its energy, but on where material travels, how long it remains in the environment, and how societies are positioned relative to it. Understanding eruption scale transforms volcanoes from isolated events into part of a broader Earth system. Each eruption adds data to a long record, helping scientists recognize patterns, probabilities, and limits. This perspective shifts attention away from fear and toward comprehension, seeing volcanic power as something measurable, comparable, and governed by physical constraints. Volcanic danger is not limited to the moment of eruption. In many regions, the most destructive effects occur later, when volcanic material interacts with water. These secondary processes can unfold hours, days, or even years after an eruption, often catching communities off guard because the volcano itself appears quiet. One of the most significant of these hazards is the lahar. Lahars are fast-moving flows made of water mixed with volcanic ash, soil, and rock fragments. They behave like thick, heavy mud, capable of traveling long distances along river valleys. Their power comes not from heat, but from mass and speed. Lahars can be triggered in several ways. During an eruption, melting snow or ice on a volcano slopes can suddenly release large volumes of water. Heavy rainfall can mobilize loose ash deposits long after an eruption has ended. Even the collapse of a crater lake can send water rushing downhill, entraining volcanic debris as it moves. Unlike lava flows, lahars follow existing drainage paths. Rivers and valleys become natural channels that guide them directly toward populated areas. Because these paths are often the same ones used for farming and settlement, lahars pose a serious risk to communities far from the volcano's summit. Water can also interact with volcanic systems in more subtle ways. Ash falling into rivers can block channels, forming temporary dams. When these dams fail, sudden floods can occur downstream. Fine ash can contaminate water supplies, clog filtration systems, and alter river chemistry, affecting ecosystems and human use. Coastal volcanoes introduce another layer of complexity. Underwater eruptions or volcanic collapses into the sea can displace large volumes of water, generating waves that travel outward. These events are not driven by seismic motion alone, but by rapid changes in seafloor shape. What makes water-related volcanic hazards particularly challenging is their persistence. Ash deposits can remain unstable for years. Seasonal rains can repeatedly reactivate them, producing multiple hazardous events long after the eruption itself has faded from memory. The danger becomes episodic rather than singular. Managing these risks requires understanding landscapes as systems, not just volcanoes as isolated features. Monitoring rainfall, river channels, and sediment buildup becomes as important as tracking magma movement. In many regions, hazard planning focuses more on post-eruption water flows than on lava itself. This interaction between volcanoes and water highlights a broader pattern. Volcanic eruptions set processes in motion that continue to evolve with weather, terrain, and time. The most visible event may pass quickly, but its influence can persist, reshaping environments in quieter but equally powerful ways. Volcanoes are not unique to Earth. When scientists began exploring other planets and moons, they discovered that volcanic activity is a common outcome wherever internal heat, pressure, and suitable materials exist. Studying volcanoes beyond Earth helps place our own planet in a broader context and reveals which aspects of volcanism are universal and which are specific to Earth's conditions. On Mars, vast volcanic structures dominate large regions of the surface. Some of these volcanoes are far larger than anything found on Earth. Their immense size reflects differences in planetary structure. Mars lacks active plate tectonics, so magma rising from deep sources remains fixed beneath one location. Over long periods, repeated eruptions build massive volcanoes without being displaced by plate motion. Martian lava flows suggest relatively fluid magma, similar to basaltic lava on Earth. The low gravity of Mars also allows lava to spread more easily, contributing to the broad shapes observed. Although most Martian volcanoes appear inactive today, their preserved forms provide a record of volcanic processes operating over billions of years. One of the most striking examples of extraterrestrial volcanism is found on Io, a moon of Jupiter. Io is the most volcanically active body in the solar system. Its activity is driven not by internal heat left over from formation, but by tidal forces. As Io orbits Jupiter, gravitational stretching and squeezing generate heat inside the moon, melting rock and driving continuous volcanic eruptions. Volcanoes on Io behave differently from those on Earth. Some eruptions eject lava hundreds of kilometers above the surface due to low gravity and extreme internal pressure. The lava itself includes materials rarely seen on Earth, shaped by Io's unique chemistry and environment. Volcanic features also appear on Venus, though they are harder to observe due to its thick atmosphere. Radar imaging reveals vast plains covered by lava flows and structures that resemble volcanic domes and shields. Venus lacks plate tectonics like Mars, suggesting its volcanic history was shaped by long-term buildup and release of internal heat. Studying these planetary examples helps scientists understand which volcanic processes depend on water, atmosphere, and plate motion, and which arise simply from heat and pressure. Earth's volcanism is distinctive because it combines all these elements, producing a wide range of behaviors. By comparing volcanoes across the solar system, scientists gain insight into planetary evolution. Volcanism becomes a tool for understanding how planets cool, how surfaces renew themselves, and how internal energy escapes into space. Earth's volcanoes are part of this larger family, shaped by the same fundamental physics acting under different conditions. Volcanoes are often associated with moments of sudden destruction, but their most important role unfolds quietly over immense spans of time. Long after eruptions end and lava cools, volcanic activity continues to influence the shape, chemistry, and evolution of the planet. Seen across geological timescales, volcanoes are builders as much as they are destroyers. Much of Earth's solid surface exists because of volcanism. New crust is created continuously along mid-ocean ridges, where magma rises and solidifies as tectonic plates pull apart. Over millions of years, this process adds vast areas of oceanic crust, slowly recycling material from the mantle to the surface. Without this steady volcanic construction, the planet's surface would look very different. Volcanic activity also plays a key role in building continents. Repeated eruptions deposit layers of lava and ash that thicken crust over time. In some regions, volcanic arcs formed at subduction zones have collided with continents, becoming permanently attached. These processes add material to continents, reshaping their size and structure across deep time. Erosion works alongside volcanism, breaking down volcanic rock and redistributing it through rivers, oceans, and wind. Minerals released from weathered lava become part of soils and sediments, eventually contributing to new rock formations. This cycle links volcanism with surface processes, tying Earth's internal activity to landscapes and ecosystems. Volcanoes also influence the long-term composition of the atmosphere and oceans. Gases released during eruptions contribute carbon, sulfur, and water vapor to the atmosphere. Over geological time, these emissions have helped regulate Earth's climate by participating in cycles that control temperature and chemical balance. Volcanic gases interact with oceans, influencing acidity and nutrient availability. Massive volcanic episodes in Earth's past have coincided with major environmental transitions. Large-scale eruptions can alter atmospheric composition for extended periods, stressing ecosystems and driving evolutionary change. These events are rare, but their influence can be detected in the fossil record, where shifts in species diversity align with periods of intense volcanism. Even when volcanoes are inactive, their presence continues to matter. Ancient volcanic rocks record information about past conditions inside the Earth, including temperature, pressure, and chemical composition. By studying these rocks, scientists reconstruct how the planet has evolved internally over billions of years. Seen in this broader context, volcanoes are agents of planetary renewal. They move material from deep inside the Earth to the surface, release energy accumulated over long periods, and participate in cycles that shape climate, landforms, and life itself. Their influence extends far beyond individual eruptions, woven into the slow transformation of the planet. Volcanic eruptions are often remembered for the life they disrupt, yet over longer timescales they also create conditions that allow life to recover and adapt. The relationship between volcanoes and living systems is complex, shaped by cycles of disturbance and renewal rather than permanent loss. In the immediate aftermath of an eruption, conditions are harsh. Lava covers the ground, ash buries vegetation, and gases alter air and water quality. Many organisms cannot survive these sudden changes. Habitats are fragmented or erased, and local ecosystems may collapse temporarily. From a short-term perspective, volcanic activity appears purely destructive. Over time, however, recovery begins. Volcanic landscapes provide fresh surfaces where life can establish itself again. Microorganisms and hardy plants are often the first to arrive. They break down volcanic rock, contribute organic material, and begin forming soil. This early stage of ecological development is slow, but it sets the foundation for more complex communities. As soil develops, plant diversity increases. Insects, birds, and other animals follow, drawn by new resources. This process, known as ecological succession, unfolds over years to centuries. Each stage prepares the environment for the next, gradually rebuilding ecosystems that can be as rich as, or sometimes richer than, those that existed before. Volcanic soils play an important role in this recovery. Minerals released from weathered lava and ash provide nutrients that support plant growth. In many regions, volcanic areas become centers of biological productivity once initial disturbances pass. These fertile conditions can sustain diverse ecosystems and, later, human agriculture. Volcanic activity can also create unique habitats. Hot springs, fumaroles, and hydrothermal systems support organisms adapted to high temperatures and unusual chemical environments. Studying these organisms has expanded understanding of life's adaptability and has implications for how life might exist in extreme environments elsewhere in the universe. On evolutionary timescales, volcanism can act as a selective pressure. Periodic disruptions force species to adapt, migrate, or face extinction. These pressures can drive evolutionary change, influencing the development of new traits and species. In this way, volcanic activity contributes indirectly to biodiversity patterns observed today. The interaction between volcanoes and life demonstrates resilience. While eruptions can cause immediate damage, they also reset ecological systems, creating opportunities for renewal. Life does not simply return to volcanic landscapes. It reorganizes, adapts, and evolves in response to the conditions left behind. Among all volcanic hazards, pyroclastic flows are the most dangerous, not because they are dramatic, but because they are unforgiving. These flows are fast-moving mixtures of hot gas, ash, and fragmented rock that travel along the ground, driven by gravity and density rather than explosive force alone. Once they form, escape is nearly impossible. Pyroclastic flows originate when an eruption column becomes unstable. During an explosive eruption, hot gas and ash rise high into the atmosphere. If the column grows too heavy or loses upward momentum, it collapses inward. The material does not fall straight down. Instead, it spills outward and downward, hugging the terrain and accelerating rapidly. Temperature is a defining feature of these flows. They are often hot enough to ignite organic material and cause fatal injuries within seconds. Unlike lava, which moves slowly and visibly, pyroclastic flows arrive suddenly and without warning. Their speed comes from a combination of gravity and internal turbulence, allowing them to move faster than a person can run. The composition of a pyroclastic flow is equally important. Fine ash particles remain suspended within hot gas, reducing friction with the ground. This makes the flow behave almost like a fluid, allowing it to surge over obstacles, climb hills, and spread across wide areas. Valleys and low-lying regions become natural pathways, directing flows towards settlements. One of the most misunderstood aspects of pyroclastic flows is that they do not require an enormous eruption to form. Even moderate eruptions can generate column collapse under the right conditions. This makes them particularly dangerous, as their occurrence is not limited to the largest volcanic events. Historical evidence shows that pyroclastic flows are responsible for many volcanic fatalities. They leave behind characteristic deposits, layers of ash and fragmented rock that blanket landscapes uniformly. These deposits often preserve evidence of sudden burial, indicating how quickly the flows arrived. Survival is rare because the danger is multifaceted. Extreme heat causes immediate injury, fine ash damages lungs, and toxic gases reduce oxygen availability. Even brief exposure can be fatal. Sheltering in buildings offers little protection, as flows can infiltrate enclosed spaces through openings. Modern hazard planning treats pyroclastic flow zones with special caution. Evacuation areas are designed based on topography and past deposits, recognizing that once a flow begins, there is no safe response except distance. Early evacuation is the only effective protection. Pyroclastic flows reveal an important truth about volcanic risk. The greatest danger often comes not from what can be seen approaching, but from processes that move faster than perception allows. Understanding these flows shifts attention from spectacle to mechanics, highlighting why volcanic safety depends on preparation rather than reaction. Not all volcanic danger is loud or visible. Some of the most serious volcanic hazards cannot be seen at all. Volcanic gases are released quietly, sometimes without eruptions, and they can affect areas far beyond the crater. Understanding these gases is essential for understanding why volcanoes can be dangerous even when they appear calm. The most common volcanic gas is water vapor, released as steam. By itself, it is not dangerous. However, volcanoes also emit carbon dioxide, sulfur dioxide, and smaller amounts of other gases. These gases originate from magma deep underground and are released as pressure decreases during ascent or through cracks in the crust. Carbon dioxide is particularly dangerous because it is heavier than air. In low-lying areas, it can accumulate without being noticed. Unlike smoke or ash, it has no color and no smell. When concentrations become high, oxygen is displaced. People and animals can lose consciousness without warning, even though the environment appears normal. Sulfur dioxide behaves differently. It has a sharp odor and reacts with moisture in the air to form acidic compounds. These can irritate the eyes, skin, and respiratory system. When sulfur-rich gases enter the atmosphere, they can contribute to acid rain and influence air quality over large regions. Volcanic gas release does not always signal an eruption. Some volcanoes emit gases continuously through fumaroles, cracks, and soil. Changes in gas composition or emission rate can indicate magma movement, but steady gas release may persist for years without surface activity. This makes gas hazards difficult to assess without careful monitoring. Gases can also travel underground. In some volcanic regions, carbon dioxide migrates through fractures and emerges far from the main vent. These areas may show little surface indication of danger. Historically, such gas releases have caused sudden fatalities in otherwise quiet landscapes. From a scientific perspective, gas emissions provide valuable insight into volcanic systems. Measuring gas ratios helps scientists infer magma depth, pressure changes, and chemical evolution. At the same time, these measurements guide public safety decisions by identifying areas where invisible hazards may exist. Volcanic gases demonstrate that danger is not limited to eruptions. Volcanoes influence their surroundings continuously, releasing substances that interact with air, water, and life. Recognizing these hazards shifts attention away from dramatic moments and toward long-term awareness and monitoring. Why all lava does not behave the same. Lava may look similar once it cools into dark rock, but while it is molten, its behavior can vary dramatically. These differences come from the chemical makeup of the magma and the conditions under which it reaches the surface. Understanding lava types explains why some eruptions spread gently across land while others pile up, collapse, or explode nearby. The most common lava on Earth is basaltic lava. It forms from magma that is low in silica and relatively rich in iron and magnesium. This composition makes basaltic lava fluid and mobile. When it erupts, gas can escape easily, reducing internal pressure. As a result, basaltic eruptions are often calm, producing long lava flows rather than violent explosions. Basaltic lava is responsible for building large shield volcanoes and extensive lava plains. It can travel far from its source before cooling, sometimes forming networks of tubes beneath the surface that allow lava to move efficiently over great distances. These flows reshape landscapes gradually, covering large areas without sudden destruction. In contrast, andesitic lava contains more silica. This increased silica content raises viscosity, making the lava thicker and slower moving. Gas escapes less easily, allowing pressure to build within the magma. Andesitic lava is commonly associated with stratovolcanoes and more explosive eruption styles. Andesitic eruptions often alternate between lava flows and explosive events. Lava may emerge slowly, forming short, thick flows that remain close to the vent. At other times, trapped gas fragments the magma, producing ash and pyroclastic material. This mixed behavior reflects the intermediate nature of the magma. The most silica-rich lava type is rhyolitic lava. Rhyolitic magma is highly viscous, resisting flow almost entirely. Gas becomes strongly trapped, making explosive eruptions much more likely. When rhyolitic lava does reach the surface, it moves extremely slowly, often forming domes rather than flowing outward. Rhyolitic eruptions can produce large volumes of ash and are commonly associated with caldera-forming events. Because the magma is thick and gas-rich, pressure builds over long periods, releasing energy suddenly when failure occurs. These eruptions are rare but can have wide-reaching consequences. Temperature also influences lava behavior. Hotter lava flows more easily than cooler lava, even if their compositions are similar. As lava cools during ascent or after reaching the surface, viscosity increases, changing how it spreads and solidifies. Crystals suspended in lava further affect movement. As magma cools and crystals grow, they interfere with flow, increasing resistance. Over time, a lava flow may transition from fluid to rigid, even without a change in composition. By studying lava types, scientists gain insight into magma sources, storage conditions, and eruption potential. Lava is not just molten rock escaping the Earth. It is a record of chemical history and physical processes unfolding beneath the surface. After understanding how volcanoes work, how they erupt, and how scientists monitor them, a natural question remains. If so much information is available, why can't eruptions be predicted with complete certainty? The answer lies in the complexity of volcanic systems and the limits of how precisely natural processes can be measured. Volcanoes do not behave like machines with fixed settings. Each system is shaped by unique geometry underground. Magma chambers are not simple cavities. They are networks of pockets, fractures, and partially molten regions that change over time. Pressure, temperature, gas content, and rock strength all interact in ways that are difficult to observe directly. Monitoring provides signals, not guarantees. Increased seismic activity may indicate magma movement, but magma can move without erupting. Ground inflation may suggest pressure buildup, yet that pressure can later dissipate through cracks without reaching the surface. Gas emissions may rise, fall, or change composition as pathways open and close underground. This uncertainty means scientists focus on forecasting rather than prediction. Forecasting assesses the likelihood of different outcomes over time. It asks whether conditions are becoming more favorable for eruption, not exactly when or how one will occur. This approach reflects the reality that volcanic systems evolve gradually and nonlinearly. False alarms are a known challenge. Evacuating populations based on warning signs that do not lead to eruptions can cause economic disruption and reduce public trust. At the same time, waiting too long can increase risk. Balancing these outcomes requires careful judgment informed by experience, data, and local conditions. Some volcanoes provide clearer signals than others. Systems with shallow magma storage and frequent eruptions are easier to interpret. Others remain quiet for long periods, offering few clues before activity resumes. This variability limits how universal prediction methods can be. Advances in technology continue to improve monitoring. High-resolution satellites, better seismic networks, and improved gas sensors provide more detailed data than ever before. Computer models integrate these observations to simulate possible scenarios, helping scientists narrow uncertainty ranges. Even with these tools, prediction will never be perfect. Volcanoes are part of a dynamic Earth system shaped by processes that operate over vast scales of time and space. Understanding this uncertainty is not a failure of science. It is an honest recognition of how complex natural systems behave. By framing volcanic forecasting as probability rather than certainty, scientists and communities can make better decisions. The goal is not to eliminate risk, but to manage it intelligently, using the best available knowledge while respecting the limits of prediction. It often feels as though volcanic activity is increasing. Images of glowing lava, towering ash clouds, and evacuations appear frequently across news platforms and social media. Eruptions that might once have gone unnoticed now seem constant and urgent. To understand whether this reflects a real change in Earth's behavior, it is necessary to separate geological reality from human perception. From a long-term scientific perspective, volcanism does not operate on yearly or even century-scale trends. Volcanoes are driven by plate motion, mantle heat, and internal pressure systems that evolve over thousands to millions of years. When viewed across these timescales, Earth's overall volcanic activity remains relatively steady. Short-term clusters of eruptions are normal and have occurred repeatedly throughout geological history. What has changed dramatically is how eruptions are observed. Modern satellites continuously scan the planet, detecting thermal signals, ash plumes, and gas emissions in near real time. Seismic networks register even minor volcanic earthquakes. As a result, events that would once have been remote, brief, or unnoticed now receive global attention within hours. Recent eruptions illustrate this shift clearly. In the early 2020s, a powerful underwater eruption in the South Pacific sent pressure waves through the atmosphere that were recorded worldwide. The event appeared unprecedented to many observers, yet its underlying processes followed known physical principles: rapid gas expansion, interaction with seawater, and efficient energy transfer into the atmosphere. What made it feel extraordinary was not new physics, but unprecedented global observation. Similarly, prolonged eruptions in regions such as the Canary Islands and Iceland drew sustained attention because they unfolded slowly and visibly. Lava advanced meter by meter, monitored continuously by drones, satellites, and ground instruments. These eruptions were not unusually energetic in geological terms, but they were unusually well documented. The science behind them was familiar. The visibility was new. Human factors amplify this perception. Global population growth has placed more people near volcanic regions, increasing the social impact of even moderate eruptions. Air travel routes intersect ash-prone skis, turning eruptions into international disruptions. Media coverage prioritizes imagery and immediacy, reinforcing the sense that volcanic activity is escalating. Climate change is sometimes suggested as a cause of increased volcanism, while localized effects, such as glacial melting reducing pressure on crustal systems, can influence individual volcanoes. There is no evidence of a global increase in volcanic activity driven by climate. Deep Earth processes remain the dominant controls. Scientists studying eruption databases see no clear upward trend in eruption frequency when detection bias is accounted for. What has increased is awareness, not activity. Earth is not becoming more volatile. Humanity is becoming more observant. Understanding this distinction is important. It grounds discussion in data rather than impression and highlights how modern technology reshapes perception of natural processes. Volcanoes behave today much as they have for millennia. What has changed is our ability to watch them closely, continuously, and collectively. After centuries of observation and decades of advanced monitoring, volcanoes are among the best-studied natural systems on Earth. And yet, some of their most important behaviors remain only partially understood. This is not because science has failed, but because volcanoes operate within complex systems that are difficult to observe directly. What remains unknown is just as important as what is known. One major uncertainty lies in the exact structure of magma systems underground. While the idea of a single, large magma chamber is useful for explanation, reality is far more complicated. Magma often exists in networks of partially molten zones, crystal-rich regions, and small pockets connected by fractures. These structures change over time, making it difficult to determine where magma is stored and how it will move. Another open question concerns eruption triggers. Scientists can identify conditions that make eruptions more likely, such as rising magma, increasing gas pressure, or surface deformation. But the precise moment when a system fails remains unpredictable. Small changes can stabilize magma or push it toward eruption, and these changes may occur at scales too fine to detect with current instruments. The role of fluids other than magma also remains an active area of research. Water, carbon dioxide, and other volatiles influence melting, pressure buildup, and eruption style, but their movement through rock is complex. Fluids can migrate independently of magma, altering conditions without obvious warning signs at the surface. There are also unanswered questions about long-term volcanic cycles. Some volcanoes alternate between active and quiet periods over thousands of years, while others remain dormant for much longer. The mechanisms controlling these cycles, whether related to mantle supply, crustal structure, or external stress, are still being explored. Volcanoes that do not erupt frequently present particular challenges. Limited eruption records make it harder to interpret monitoring signals. A change that would be insignificant at one volcano might be meaningful at another. This variability limits how universally predictive models can be applied. Even the interaction between volcanoes and climate contains uncertainties. While the cooling effects of major eruptions are well documented, the full range of feedbacks involving oceans, clouds, and ecosystems is still being studied. Small differences in eruption timing or material distribution can lead to different outcomes. These unknowns are not gaps to be ignored. They are active frontiers of research. Advances in imaging, data analysis, and modeling continue to refine understanding, but volcanoes remind scientists that Earth systems resist complete simplification. Recognizing what is not yet known encourages caution and humility. It reinforces why volcanic science relies on probabilities rather than certainties, and why continuous observation matters. Knowledge grows, but uncertainty remains a natural part of studying a planet that is still very much alive. Some volcanic eruptions are remembered because they destroyed nearby cities. Others are remembered because they altered conditions far beyond their immediate surroundings. The largest eruptions in Earth's recent history belong to the second category. Their importance lies not only in their violence, but in how they reveal the upper limits of volcanic systems and their ability to influence climate, ecosystems, and human history at the same time. One of the most significant eruptions ever documented occurred in the early 19th century at Mount Tambora. Before its eruption, Tambora was a large stratovolcano, towering over the surrounding landscape. Over time, gas-rich magma accumulated beneath it, evolving slowly and storing enormous pressure. When the eruption finally occurred, the release was catastrophic. The eruption expelled vast quantities of ash and gas into the atmosphere, forming an eruption column that reached extreme heights. Large portions of the volcanic structure collapsed, leaving behind a massive caldera. Pyroclastic flows swept across the surrounding regions, while ash fall buried landscapes far from the volcano itself. The immediate destruction was severe, but the longer-term consequences were even more remarkable. The gases released into the upper atmosphere spread globally, reducing the amount of sunlight reaching Earth's surface. This led to a period of unusual cooling, disrupting weather patterns across multiple continents. Crop failures, food shortages, and social unrest followed in regions thousands of kilometers from the eruption site. Tambora demonstrated that a single volcanic event could influence global climate and human systems simultaneously. Another eruption often discussed in this context is the much older Lake Toba event. Unlike Tambora, which was witnessed and recorded by humans, the Toba eruption occurred long before written history. Its scale is inferred from geological evidence rather than direct observation. Ash layers from this eruption are found across wide regions, indicating an event of extraordinary magnitude. The Toba eruption released such a large volume of material that it reshaped the landscape permanently, forming a vast caldera that later filled with water. Evidence suggests that global temperatures dropped for an extended period afterward, placing stress on ecosystems worldwide. While the exact impact on early human populations remains debated, the eruption clearly represents one of the most powerful volcanic events of the last several 100,000 years. What unites these eruptions is not just their size, but their mechanics. Both followed the same physical principles discussed earlier: gas buildup, pressure release, fragmentation, and collapse, operating at extreme scale. These events show that volcanic power increases nonlinearly. Once a system grows large enough, its effects extend far beyond the eruption site. Studying the largest eruptions helps scientists understand the limits of volcanic behavior. It provides context for assessing modern risks and reminds us that Earth's most transformative events often arise from processes that build quietly over long periods before releasing their energy all at once. Not all world-changing volcanic events arrive as single, explosive eruptions. Some of the most profound transformations in Earth's history were driven by volcanism that unfolded slowly, quietly, and relentlessly over long periods of time. These events are known as flood basalt eruptions, and their impact comes from duration and volume rather than sudden violence. Flood basalts occur when enormous quantities of low-viscosity magma rise from deep within the mantle and spread across the surface through extensive fissures. Instead of building tall volcanoes, the lava pours out repeatedly, forming vast layers that stack over time. Each individual eruption may appear modest, but together they cover regions the size of countries. Two of the most significant flood basalt provinces on Earth are the Siberian Traps and the Deccan Traps. These regions are defined not by a single crater, but by thousands of lava flows preserved in thick sequences of solidified basalt. What makes flood basalts especially important is their timing. The Siberian traps formed around the same time as the largest mass extinction in Earth's history, an event that eliminated the majority of marine and terrestrial species. Rather than a single catastrophic blast, the extinction appears linked to prolonged environmental stress caused by sustained volcanic activity. As lava continued to erupt over hundreds of thousands of years, enormous amounts of volcanic gases were released into the atmosphere. Carbon dioxide increased global temperatures, while sulfur compounds affected air quality and acid rain. Oceans absorbed these changes, becoming warmer and more acidic. Ecosystems were not destroyed in a single moment. They were gradually pushed beyond their limits. The Deccan traps present a similar story, though the details differ. These eruptions occurred over an extended period during a time of significant biological turnover. Lava flows spread across much of what is now India, releasing gases continuously and altering climate patterns. The timing overlaps with the extinction of the dinosaurs, suggesting volcanism played a major role in shaping the environmental conditions of that era. Flood basalts challenge the idea that geological danger must be sudden to be severe. Their effects accumulate. Each eruption adds a small amount of stress to the climate system, the oceans, and the biosphere. Over long timescales, this steady pressure becomes transformative. From a scientific standpoint, flood basalts reveal how Earth releases internal heat in different modes. Instead of explosive release, energy escapes gradually through vast outpourings of lava. The consequences depend not on speed, but on persistence. Understanding flood basalts expands the definition of volcanic risk. It shows that the most influential eruptions are not always those that capture immediate attention. Some operate slowly enough to reshape life itself, leaving behind records written not in disaster reports, but in the fossil record and the chemistry of ancient rocks. In the modern world, volcanic activity no longer exists in isolation from human systems. Cities, transportation networks, energy infrastructure, and global supply chains now intersect with volcanic regions in ways that amplify consequences. A moderate eruption today can create effects far beyond what the same event would have caused centuries ago, not because volcanoes have changed, but because human dependence has. Many of the world's largest cities lie within reach of active volcanic systems. This is not coincidence. Fertile soils, access to water, and favorable geography have historically attracted settlement. Over time, these settlements grew into dense urban centers, placing millions of people within zones shaped by volcanic processes. As cities expand, exposure increases, even when eruption frequency remains constant. Modern infrastructure adds another layer of vulnerability. Power lines, communication systems, and transportation corridors are sensitive to ash, gas, and ground deformation. Fine ash can damage electrical equipment, contaminate water systems, and reduce visibility. Even small ash clouds can ground aircraft, disrupting travel and trade across continents. Aviation is particularly vulnerable. Volcanic ash is abrasive and can damage jet engines when ingested. Because ash clouds are not always visible on radar, airspace closures must err on the side of caution. A single eruption can therefore affect global air traffic, highlighting how interconnected modern systems have become. Supply chains are similarly exposed. Ports, factories, and shipping routes may lie far from volcanoes, yet still be affected by disruptions upstream. Delays ripple outward, affecting industries and consumers far from the eruption site. These indirect effects often exceed the immediate physical damage caused by the volcano itself. Technology also provides new tools for resilience. Early warning systems, satellite monitoring, and rapid communication allow authorities to respond faster than ever before. Evacuations can be organized, airspace can be managed, and infrastructure can be protected when warning signs are recognized in time. This does not eliminate risk, but it transforms how societies cope with it. The challenge lies in balancing development with awareness. As populations grow and technology advances, volcanic risk becomes a matter of planning rather than avoidance. Decisions about land use, infrastructure placement, and emergency preparedness shape outcomes long before any eruption occurs. Volcanoes in the modern world reveal a deeper truth about risk. The hazard itself may be natural, but the scale of impact is often human-made. Understanding this relationship allows societies to reduce vulnerability, not by controlling volcanoes, but by adapting intelligently to the environments they inhabit. As scientific understanding of volcanoes has improved, a natural question has followed. If we can monitor volcanoes and understand their behavior, can we also control them? Throughout history, humans have attempted to influence volcanic activity in various ways. These efforts reveal both human ingenuity and the firm limits imposed by natural forces. The idea of controlling volcanoes often begins with lava. Lava flows are visible, slow-moving compared to other volcanic hazards, and appear manageable. In a few rare cases, humans have successfully altered the path of lava to protect specific structures. Barriers have been built, channels dug, and cooling techniques applied to slow or redirect advancing flows. These interventions work only under very specific conditions: fluid lava, gentle slopes, and sufficient time to act. Even in these cases, control is limited. Redirecting lava does not stop an eruption, it merely changes where lava travels. The energy driving the eruption remains unchanged, and intervention only succeeds on small scales. Large or explosive eruptions cannot be influenced in this way. Lava diversion is a local response, not a solution. Attempts to influence volcanic systems at depth are far more limited. The pressures, temperatures, and volumes involved inside magma systems exceed anything humans can realistically manipulate. Drilling into magma chambers is not feasible, and releasing pressure intentionally would likely increase danger rather than reduce it. The internal structure of volcanic systems is too complex and too powerful for direct control. There have also been proposals to trigger small eruptions intentionally to prevent larger ones. These ideas misunderstand how volcanic systems work. Pressure does not behave like air in a container that can be safely vented. Disturbing a magma system could destabilize it, increasing the risk of uncontrolled eruption rather than reducing it. What humans can control effectively is exposure, not volcanoes themselves. Land use planning, hazard zoning, early warning systems, and evacuation protocols have saved countless lives. By choosing where and how to build, societies influence outcomes long before volcanic activity becomes visible. Technology strengthens this approach. Real-time monitoring allows authorities to act on evidence rather than guesswork. Communication systems spread warnings quickly. Infrastructure design can reduce vulnerability to ash, gas, and ground deformation. These measures accept volcanic power rather than challenge it. The question of control ultimately reveals a deeper lesson. Volcanoes operate on scales of energy and time that dwarf human capability. Scientific progress increases understanding, not dominance. The most effective strategy is not intervention, but adaptation, learning to coexist with active geology. By recognizing these limits, societies make wiser decisions. Control gives way to preparation, and ambition is replaced by respect for natural systems that cannot be commanded, only understood. Volcanoes feel dramatic because eruptions happen suddenly, but the forces that create them move at an almost unthinkably slow pace. To understand the future of volcanism, it is necessary to step far beyond human lifetimes and look at Earth as a long-evolving system. The future of volcanoes is not about the next eruption, but about how the planet continues to release internal heat over millions of years. Earth's interior is still hot because of heat left over from its formation and from the slow decay of radioactive elements. This heat must escape. Volcanoes are one of the main pathways through which that energy is released. As long as Earth remains geologically active, volcanism will continue in some form. In the near future, measured in centuries, volcanic activity is expected to remain broadly similar to what is observed today. The same tectonic boundaries will continue to generate magma. Subduction zones will keep producing explosive volcanoes. Mid-ocean ridges will quietly create new crust beneath the seas. Hotspots will continue building volcanic chains as plates move overhead. Over longer timescales, changes become more noticeable. Tectonic plates shift position, collide, and break apart. New subduction zones form while others shut down. Volcanic arcs migrate. Regions that are volcanically active today may eventually fall silent, while new volcanic regions emerge elsewhere. This redistribution happens slowly, but it reshapes the global pattern of volcanism. The formation of future supercontinents will also influence volcanic activity. When continents assemble into large landmasses, heat can become trapped beneath thick crust. This can lead to extensive volcanic episodes when that heat is eventually released. Past flood basalt events suggest that these periods of reorganization can coincide with intense volcanism. Earth's volcanic future is also tied to how the planet cools. Over billions of years, Earth will gradually lose internal heat. As this happens, volcanic activity will decrease. This process is extremely slow, but other planets provide clues. Mars, which cooled faster due to its smaller size, shows evidence of ancient volcanism but little current activity. Earth is far from this stage, but it illustrates the long-term trajectory. Human influence does not significantly alter this deep future. While surface changes can affect local stress conditions, the main drivers of volcanism lie far below any direct human reach. Volcanoes will continue according to internal planetary processes, largely independent of civilization. Thinking about the future of volcanism reframes how volcanoes are viewed. They are not temporary threats or isolated hazards. They are expressions of Earth's ongoing evolution. Each eruption is part of a long process that began billions of years ago and will continue long after modern societies change or disappear. Understanding this timescale brings perspective. Volcanoes are not signs of instability in a failing planet. They are signs of a planet that is still active, still moving, and still releasing the energy that shaped it from the beginning. Volcanoes are not isolated disasters. They are part of a continuous planetary system through which Earth releases internal heat and reshapes its surface over long spans of time. From magma formation to eruption, the processes follow physical rules. Pressure builds, energy moves upward, and material circulates. Whether an eruption is gentle or extreme depends on scale, not randomness. Volcanoes behave consistently within the laws governing a planet that is still active. Volcanic activity links Earth's interior to its surface and atmosphere. It creates land while eroding it, disrupts climate briefly while contributing to long-term balance, and presents risk while also providing fertile ground and resources. These effects are not contradictions, but outcomes of the same system acting over different timescales. Modern science has replaced fear with context. Monitoring and long-term observation allow societies to prepare rather than react. Control remains impossible, but understanding changes how risk is managed. Volcanoes are not signs of instability. They are signs of a planet still releasing energy. Seen in this light, volcanoes become easier to understand. They are expressions of Earth's slow evolution, governed by rules that extend far beyond human experience. At this point, the exploration is complete. Everything essential has been covered, and the system behind volcanoes now stands clearly explained. If you are still awake, this is a good moment to rest. If this exploration added value, you can support the channel by liking the video, subscribing, and sharing your thoughts. Other videos and playlists on your screen continue this journey, one curious soul at a time.